This video training program will provide you with an introduction to the electrical systems of the XJ-6. The program is divided into several sections. The first section outlines the development from electrical to electronic circuits. A section of basic electronics covers some of the fundamental electronic concepts. At the heart of the electrical system is the central processor unit, and we'll be looking at two of the many circuits which are controlled by it: the direction indicator circuit and the interior lighting circuit. In Section 5, you'll see the new layout of electrical harnesses in the XJ-6, and we'll look at how the central processor unit fits in. We also look at the new types of connectors. The new Jaguar diagnostic system is the subject of the last section. And finally, a glossary of electronic terms is included. Electrical and electronic circuits are simply routes through which current is fed from a power source to the unit needing power and then on to Earth. An electronic circuit is only different from an electrical circuit because of the components used to control and direct power. Electronic circuits generally use small solid-state devices as opposed to the electromechanical devices used in electrical circuits. So, to begin, let's see how electrical circuits developed to become electronic. Historically, the way in which circuits have changed can be illustrated using four circuits. Circuit 1, a very basic circuit with a power supply, conductive cabling, a fuse, a switch, and the unit needing power. Circuit 2, in which a relay has been added. After relays were invented, they were commonly included in circuits. Circuit 3, the same as Circuit 2, except that the switch is on the negative side of the circuit nearest the Earth. And Circuit 4 shows a transistor in the central processor unit, controlling the relay. We're going to look at each circuit in turn to see how the different components have been utilized in them. In this circuit, big switches have to be used. Here's one of the switches that would have been used to turn on the headlamps. Why do you think it's so large? No, this isn't a reasonable answer. Switch has However, the switch is large because all the current required by the bulb in the first is drawn through the switch contacts. Yes, the switch is large because it is carrying all the current and needs to be heavy-duty to prevent the contacts becoming hot or overheated, which would happen if the switch was smaller. You can see that the wiring to and from the switch is heavy-duty. Again, this is because it is carrying all the current. The addition of a relay to the circuit was the next development. This is the symbol for a relay. Two cables run from the power source to the relay. The top cable conducts a small current, approximately 1/4 amp, to energize the relay windings, and the bottom cable conducts the larger current, 5 amps, through the relay contacts and onto the bulb. In this case, it's a headlamp. If we take the relay apart, we can see the solenoid and the contacts. This is how it works. The solenoid is fed a small current which energizes the copper windings, thereby creating a magnetic field, which attracts the contacts, completing the circuit, allowing the larger current to travel to the bulb. The relay is, in effect, acting like a switch. This means that in a circuit of this type, it's the relay contacts which carry the full current load, so the driver's switch contacts can be smaller. Why can a switch used in a circuit with a relay be smaller than that used in a circuit without a relay? No, a smaller switch can be used in a circuit of this type because it only needs to carry the low current to energize the relay windings, which then allow the larger current to flow to the bulb. Yes, the switch can be smaller and lighter duty in a circuit of this type because it only has to carry enough current to energize the relay windings. Look at the fuses in the circuit. Which do you think has the greater current rating? Yes, remember that only a small current carry enough to energize the relay windings, and this is carried by so fuse 1 will be the lower rating. Fuse 2 is carrying greater current, the current which is used to supply the bulb, so it has to be a higher rating. This is the third circuit in our historical overview. Let's compare it with Circuit 2. What's the difference between these two circuits? Yes, in Circuit A, the switch is on the positive side. In Circuit A, The switch is on the positive side. This is called negative earth line switching. This reduces the amount of positive cable to and from the driver's controls. Positive cable to and from the driver's controls. In the fourth circuit, we show the next major development, the introduction of a transistor. A transistor is a solid-state device used to switch on or redirect current in a similar way to the relay we described, but it is physically smaller and is of simpler construction. It's shown here located in the central processor unit, or CPU. The CPU is situated under the glove compartment. It's a microprocessor which initiates many of the actions commanded by the driver. We'll be looking at just a few of these, the doors, some aspects of lighting, and the direction indicators, later. In circuits of this type, momentary action clicker plate switches can be used. Their contacts are much smaller than those needed in circuit 1 because they only need to carry the minute current to signal to the CPU. This circuit is activated by this switch. The CPU detects an input and responds by sending a minute current to the transistor to switch it on, which will allow current to flow through the relay windings, through the transistor, and down to the logic earth, thereby energizing the relay windings. This will close the relay contacts, allowing 12 volts to pass through the bulb to the power earth. In circuits of this type, the driver's switch need only be small, like a momentary action clicker plate switch. All ground connections on microprocessors and logic circuits are taken to a wire which is connected to the battery earth. This minimizes any voltage changes on the ground connections of sensitive electronic circuits. This is called the logic earth and is located on the bulkhead at the closest point to the battery negative cable. All logic earth cables are colored black and pink. In the new Jaguar car, the use of transistors in circuits and a central processor unit is a significant advance, and we'll be looking at two circuits which are controlled by the CPU, the direction indicators and the interior lights. But next, some basic electronics. This section will serve as an introduction to conductors, non-conductors, semiconductors and transistors. An electrical circuit is made from conductive material such as copper wire. These wires are insulated by a non-conductive material such as plastic. Here's a list of some commonly known substances. Can you say which of these materials are conductors and which are non-conductors? Yes, you're quite right. Gold, mercury and lead are all very good conductors of electrical current, whereas wood, paper, carbon and rubber are very poor or non-conductors of electricity. All conductors have a tendency to resist the passage of electrical current and to convert electrical energy into heat energy. This is called resistance, and circuits are designed to minimize the problems that this might create. A 12-volt battery supplies power to the entire circuit. It would be natural to expect that the voltage in the circuit up to the bulb should read 12 volts. However, due to the natural resistance of the cable and possible resistance across the contacts of the switches, some of the voltage may be converted into heat energy en route. So the bulb may only receive 11.9 volts. Thin cables have a higher resistance than thick cables. Here's a measurement taken at the bulb. It reads 11.9 volts. Why do you think this volts drop has happened? This wouldn't have caused the drop in voltage. No, the larger the cross-sectional area of the cable, the less the drop in voltage. There's a natural drop in voltage through every cable due to resistance. This is called volts drop. The longer and thinner the cable, the greater the resistance, and therefore the greater the volts that will occur. Conversely, the shorter the cable or the thicker the cross-sectional area, the less the volts drop. Having looked at conductors, let's look at semiconductors. In basic terms, a semiconductor can act as a conductor or as a non-conductor. Diodes are typical examples of semiconductors. This is the symbol for a diode. They act a bit like one-way valves. Current will only flow through the diode in the direction of the arrow. Look at this circuit. Can you say if the bulb will be on or off? The bulb will light because the diode is pointing in the direction of the current flow. Current will only flow through the diode in the direction of the arrow. Look at this circuit. Will the next bulb light? No, correct. The bulb won't light the diode because the diode is opposing the current flow. Will the bulb light in this circuit? Correct. No, the bulb won't light. Current will only flow through the diode in the direction of the arrow. Look at this last circuit. Will the bulb light? Yes, no, the current will flow through the diode in the direction of the arrow. The bulb will light. A transistor, like a relay, can be used as a switch. But unlike a relay, it is a solid-state device, which means that there are no moving parts. A transistor is a 3-lead, current-operated device. The leads are called the base, the emitter, and the collector. To operate the transistor, we must only apply a very small current to the base. This activates the collector-emitter circuit and allows a larger current to flow through the bulb and down to earth. In this diagram, the collector-emitter circuit could be overloaded if too large a bulb is used. It's for this reason that resistors are used to control current travelling to the base. If the resistor was bypassed using a test lamp, for example, one of two things could happen. The base connection will be broken and the bulb will go out, or the base connection will fuse to the collector-emitter circuit so that the bulb can't be switched off. Either of these possibilities are serious. If this was to happen, the transistor would cease to function as a switch and would not be able to control that part of the circuit. Transistors and other such electronic devices are used extensively in Jaguar circuits. Therefore, the use of test lamps to detect faults is prohibited. The Jaguar Diagnostic System, the JDS, has been designed for circuit testing and fault diagnosis. Don't use any other tools on the electronic circuits in these cars. This is the circuit diagram for the direction indicators. It shows 3 types of switches: the driver's switch, the hazard switch, the reed switches in the cancellation unit. All these switches have input lines to the central processor unit, and the central processor unit has outputs to all the other indicator accessories. The left-hand lamp relay module, the right-hand lamp relay module, the dot matrix, the instrument pack, and the audible warning unit and its speaker. Information received by the CPU is called an input, and information sent out are called outputs. We've numbered the pins on the CPU for the purpose of our identification only. The audible warning unit is housed under the glove box and is connected to a speaker under the steering column. We'll be discussing the functions of each of these components later, but first, let's look at the switches and exactly what they control. First of all, the direction indicator switch. It is a momentary action switch and will not lock or latch into any one position. To indicate a right-hand turn, the driver presses the momentary action switch upwards. It returns to its central position instantly, and the central processor unit will immediately detect the signal. The CPU has been programmed to control the indicator functions and responds to the input from the indicator switch by sending intermittent outputs to the right-hand lamp relay module, the instrument pack, and the audible warning unit. Once the indicator circuit has been activated, the CPU will monitor the 3 reed switches. These switches are housed in the cancellation unit and are carefully lined up to 3 magnets built into the steering column. As the steering column is moved, the magnets are rotated past the reed switches, which causes them to close in sequence. If the steering column is being turned right, the reed switches will be closed in the order 3, 2, 1. As each reed switch closes, signals are detected by the CPU on 3 separate input lines. The CPU knows that if the reed switches close in the order 3, 2, 1, then the steering column is being turned to the right. When the steering column is straightened up after turning right, the magnets pass back over the reed switches, closing them in the reverse order, 1, 2, 3. The CPU then knows that the maneuver has been completed and cancels outputs to all indicator accessories, thus cancelling the right-hand turn signal. Now that you've seen how the CPU activates and cancels the right-hand lamp relay module, the arrow on the instrument pack, and the audible warning unit, You should be able to state the switching and CPU procedure for a left-hand turn. The driver presses the indicator switch downwards and makes a connection to earth. The CPU will detect a signal. On which pin? No, the pin located at position 3 is used by the CPU to monitor if the driver has signalled a right-hand turn. Try again. No, the CPU will send an output to the left-hand lamp relay module at pin 1. You're looking for an input. Try again. Yes, when the driver presses the indicator switch downwards, the CPU will detect an input signal on pin 2 because an earth connection has been made. We think you should go back and look at the tutorial for the right-hand indicator circuit again. When the CPU detects a signal at pin 2, it's programmed to output 3 signals. One to the left-hand lamp relay module, activating the left side indicators, a second output to pin 14, activating the audible warning unit. Which other pin will receive an output from the CPU? No, the output to that pin activates the right-hand lamp relay module. The driver has depressed the indicator switch to turn left. You don't want to activate the right-hand indicators. Try again. No, a signal at pin 12 will make the arrow pointing to the right illuminate. The driver's turning left. Try again. No, a signal is only output on pin 11 if any of the bulbs have failed. We'll be discussing this in more detail later. Try again. Yes, the third signal that the CPU will output is at pin 13, operating the left arrow on the instrument pack in time with the sound emitted from the audible warning unit and its speaker. Let's just go through that again. The driver pushes the indicator switch down. He wants to turn left. The momentary action switch returns to its central position. The CPU, detecting a signal on pin 2, outputs signals to pins 1, 13 and 14, activating all left indicator accessories. How does the CPU know that the driver has executed the left-hand turn? The CPU does monitor switches to detect if the left-hand turn has been executed, but these switches are located in the nacelle of the steering column, not on the steering rack. The CPU monitors 3 reed switches. Yes, the CPU monitors 3 reed switches near the steering column to detect if the car has been turned left. In what order will the reed switches close if the driver is turning the steering column to the left? No, if the steering column is being turned to the left, switches will not close in the order 3, 2, 1. Watch. Yes, if the steering column is being turned left, the switches will close in order 1, 2, 3. When the steering column is straightened up after turning left, the magnets close the reed switches in the order 3, 2, 1. The CPU will then cancel outputs to the indicators. The direction indicator system includes a lane change facility. If the indicator switch is held in position for longer than 3 seconds, the CPU will not monitor the reed switches. Cancellation is achieved simply by releasing the switch. If an indicator bulb fails, a sensing circuit in the lamp relay module will output a signal to the CPU, which will ensure that the remaining bulbs stay operational. However, the driver is warned because the arrow display and the audible warning unit operate at twice their normal speed. This warning is reinforced by a symbol on the dot matrix. Finally, the hazard warning lights operated by this switch. It's a latching switch, and when pressed, it activates both indicator lamp relay modules, the audible warning unit and its speaker. The switch itself also lights up intermittently. This is the diagram for the interior lighting circuit of the Jaguar XJ-6. It shows the interior lamps, the map reading lamp, the rear seat reading lamps, and the puddle lamps. All the switches for these units are connected to the CPU. The CPU also monitors the driver's seat pad switch, the driver's and passenger's door lock latches, and the start position of the ignition switches. The reading, interior and puddle lamps are activated if the door is opened. The puddle lamps are located in the bottom of each door. The interior lamps, along with the map reading lamp, are located in the roof, and the reading lamps are housed in the back of the front seat headrests. With the exception of the puddle lamps, all these lamps can be operated manually through switches. If this reading lamp is manually operated, which pin on the CPU will detect the signal? No, this is the input from the map lamp switch. Try again. No, pin 8 is the input from the 3 passenger door switches. Try again. No, pin 7 is the input from the driver's door lock latch switch. Try again. Yes, when a passenger sitting in a back seat depresses the reading lamp switch, the CPU receives a signal on pin 4. All interior lamps and puddle lamps are activated by the door lock latch switches. There's one housed in each door. Inside the door lock latch, there's a micro switch operated by an arm pin. The arm pin will pivot forward when the door is open and backwards when it's closed. When it's in the forward position, it pushes the contacts of the micro switch together. This causes a signal to be input to the CPU and the vehicle condition monitor, the VCM. This informs the CPU that the door is open. It'll therefore switch off the interior and reading lamps after a set period of time. If the ignition is cranked before the door is closed, the VCM will identify which door is still open and display a symbol on the dot matrix. When the door is closed, the arm pin will pivot backwards, thereby opening the contacts of the micro switch, causing the signals to the VCM and CPU to be cancelled. The CPU is programmed to respond to this by operating the interior and reading lamps on a different timing. In conjunction with the driver's door lock latch switch, the CPU also monitors the driver's seat pad switch. The driver's seat pad switch is a sensor pad built into the seat. It's made of 2 sheets of copper separated by a sheet of perforated foam. When the sheets are pressed together, the copper makes contact through the holes in the foam and inputs this signal to the CPU. If both the driver's door lock latch and the driver's seat pad switch are activated, the CPU will time the lights for 15 seconds. However, if the ignition is cranked before the 15 seconds have elapsed, the CPU automatically switches all interior lamps off. If the driver opens the door but doesn't get in, the seat pad switch will not be activated. If the door is left open, the CPU will operate a 2-minute timer. If the driver's door is opened but closed before he gets in, the interior lamps are on a 15-second timer and so stay alight. True or false? Okay, the interior lamps are not on a 15-second timer. The interior lamps are on a 2-minute timer and so stay alight. True or false? Yes, you've got both parts of the question correct.
Yes,
if the driver opens the car door and closes it without getting in, the interior lights will go out immediately. The interior lamps are on a 15-second timer, but only if the driver gets in the car, which activates the sensor in the seat pad, which will input a signal to the CPU. The interior lamps are on a 2-minute timer, but only if the driver doesn't get into the car and doesn't close the door. If the driver's door were to be left open, then the 2-minute timer on the CPU would come into operation. If the driver had got into the car and closed his door, then the 15-second timer on the CPU would come into operation. If you have to diagnose any faults in this circuit, on no account use a test lamp. Always use the Jaguar diagnostic system, which is featured in a later section of this disc. The XJ-6 electrical systems harness consists of 2 side harnesses running the length of the car, joined together by the bulkhead harness which runs behind the dashboard. On this cutaway car, we'll be following the left-hand side harness and the bulkhead harness, showing the points where they're joined and the run of the harness through the body shell. Starting at the front left-hand lamp relay module, the left-hand side harness runs through the engine bay and onto the left-hand side bulkhead grommet, located in the A-post. Here there's a breakout from the side harness carrying the leads for the interior lamps and the sunroof. From here, the side harness is then run down the A-post inside the car, where it's recessed into the sill and run up to the BC post. At this point, there's another breakout of wiring which will be fed to the rear door speaker, the left-hand side door locks and the window controls. The side harness continues to run recessed into the sill up to the rear seat pan, where it's run into the heel board. There's a breakout at the heel board for the heel board speaker. The side harness continues to run under the rear seat pan, allowing another breakout which carries the connection for the fuel pump. The rest of the harness runs onto this grommet, which will be positioned in the D post. It then passes through the baffle plate grommet into the boot, where the side harness run finishes. Both side harnesses are joined together via the bulkhead harness by these connectors. The square connectors are used for signals. They're positive mate high density types, PMHDs, and the round connectors are used for power. They're positive mate Mark IV types, PM4s. In general, these types of connectors are used wherever a join in the harness is required. Both these types of connectors are male-female linked. This is the male half, and this is the female half. When joining them together, always ensure that the ramp lock mechanism is firmly in place. The bulkhead harness is run along the bulkhead behind the dashboard and carries the connections for the central processor unit and the wiring for the center console harness. The central processor unit is housed behind the glove compartment and linked into the vehicle electrical system via these connectors, a 36-way PMHD input connector and a 36-way PMHD output connector. It receives its main battery feed from the PM4 connector. The center console harness breaks out from the bulkhead harness at the center of the bulkhead and is run down the tunnel before connecting into the center console. If you're required to make any fault diagnosis on the XJ-6 vehicle electrical system, always use the Jaguar diagnostic system. This is the Jaguar diagnostic system, the JDS. It is to be used for all fault testing and diagnosis on the XJ-6. To operate, simply turn the machine on. When activated, the instructions displayed on its screen and the tools provided are all that are needed for fault diagnosis. First of all, choose the correct option relating to the suspected fault. In this example, the windscreen wiper. Now, the JDS will guide you through its diagnostic procedure. Follow its instructions correctly, and it'll provide you with a detailed fault description and a code with which you can obtain the right component to correct the fault. It'll also provide you with a printout of the fault description.